at some optimizations done on SSA Form. And there are two versions of something called value numbering. Value numbering is an example of a way to remove redundant expression, which means expressions which are performed twice or more. So let's look at this. If we have a plus b in one basic block, which dominates another, which contains the same expression, then we can remove the second a plus b. Removing an expression like that is called a redundancy elimination. And this is very simple, obviously, and it requires that we have this one dominating that one. That can be done very easily when we translate a program to SSA form. And it's done using something called hash-based value numbering. Hash-based value numbering is also used for simplifying expressions, or actually to make expressions look similar. Suppose, well, not only similar, but sometimes also simplifying. Assume a is an integer, and say we have 2 times a, and then we can change that to a shifted 1 to the left. And to recognize redundancy, it's easier if the same value is expressed with the same operator. So suppose we have a shifted once to the left and also 2 times a. Then it's useful to have them in the same format, in the same form. So that's one of the tasks done during, well, it can be done in different times, but it's typically done in the translation to SSA form, and the translation to SSA form includes hash-based value numbering, typically. Not as you will do it in the lab, because you will do the translation to SSA form, but you will see how it can be done. You will do a very minor optimization, which is similar to hash-based value numbering. Okay, we can also do a minus a and replace that with 0. However, we cannot do it always. We can only do it if a is an integer. Why not if a is a floating point number? A minus a, isn't that guaranteed to be 0? No, it's not. What else can it be? It can be not the number. If a is not the number, then the result should be not the number and not 0. Okay, here 1 times a is of course still a, even if it's not a number. But 0 times something is not necessarily 0. If a is infinity, then the result should be not a number. Okay, so we have to keep that in mind. Another form of value numbering is called global value numbering. And we will not see now how it is done, but what it can do. This is quite amazing. So what we see here, if we look at it for a while, then we will note that x and y always have the same value. But they are strictly not related. I mean, there is no assignment between x or y, but they have the same value. And this can be discovered using this algorithm. And then y can be removed. You may wonder, who will ever write code like this? Probably not so many, but this can be the result of other optimizations and of translation to 3-address code. So this occurs in reality. Actually, I had a master thesis student who implemented this algorithm in GCC, and I was very skeptical that it would affect performance in any way. But because GCC at that time was already a very mature compiler, but it did improve the performance with, in some codes, some percent. And that is really cool. Okay, so you might wonder, how can it do this? Well, the basic idea is to assume that every value produced by the same operator, that is, every addition, is assumed to produce the same value. Obviously, that cannot be true for all additions, but unless it can be proved wrong, they are still assumed to produce the same value. And it's impossible to prove that these two additions produce different values, so therefore it's concluded that they produce the same value. Common subexpression elimination. Here we can see A times B in two different, I mean three, but there are two occurrences here in the if and the else parts, and then we use A times B again. So what can we do with that? We can save A times B in a temporary variable and then use that temporary variable instead. What we also could do is to put A times B above the if statement. But in general, it's not always good to move code so that the value is needed during a longer period. Why? Because then the value must be stored somewhere, such as in a register, and then that machine register is occupied for a longer time. So what we do in this optimization is to save the value where the expression was computed and then reuse it. Why can we reuse it? Because it's available at all predecessors. This expression has, I mean, it's a control flow graph with the return statement is the last, obviously, and there are two predecessors, the then and the else basic blocks. And A times B is available in both cases, so therefore we can use it. This optimization is usually never implemented in a modern compiler. If it's written in the marketing of a compiler, it means either it's not a very modern compiler or the marketing department are not exactly informed, or they ignore some facts in order to look better. But there is actually another optimization which can do the same as this in a much nicer way, and other things as well. It's called partial redundancy elimination. In this case, we have redundancy, but it requires full redundancy, namely that A times B is available from all predecessors. Then we can remove it. This one can be removed thanks to A times B is available. Okay? And we will come to that other very soon. Another optimization which we can do is moving loop-invariant code out of loops. So the first iteration, A of I, is not redundant because, I mean, we have not read this array element before. But in the second and third, etc., we have already seen this, so why not replace it like this? Here is the same idea, that we can move a of I to before the loop and just use T instead. Actually, one of these is wrong. So what happens if A is a null pointer? Well, in this case, it will crash a bit sooner, but so it doesn't matter. If it's undefined behavior due to a null pointer, anything may happen, including crashing earlier than intended. Here, instead, it depends on whether x is equal to y. So it's not necessary that we actually will come to this, and then it would not crash unless we put it here. I mean, yeah, you see what I mean. Okay. So, partial redundancy elimination. It is obviously again about redundancy elimination, and now we have this situation where the value is only, I mean, the expression is only partially redundant. What does that mean? It means that if we go to the then case and assume there is no a times b in there, then we go here and then we go here. So a times b is evaluated once. But if we go to the else, we evaluate a times b twice. So what we can do is to insert another expression there in the then part, and well, and then a times b becomes fully redundant and we can remove it. This optimization was also created 1979 as the Lengauer-Tarian algorithm, but not by them, but by two French researchers, Morel and Renoise. Okay, what is even more interesting with partial redundancy elimination is that it can move code out of loops without knowing there is a loop. So in the first case here, I mean in the first iteration, a divided by b is not redundant, but in the second, etc., second, third, etc. Iteration, it is redundant. So what this algorithm does is to insert the expression at the predecessor, which had not that expression. And then it concludes that now a divided by b is fully redundant and can remove it. This is one of the most important optimizations, and it has been developed over the years. Initially, it was believed by some that it could not be done on SSA Form, but it can, and we will come back to that later. Another optimization, which is actually one of the very first implemented in the Fortran compiler created during 1950s, is called operator strength reduction. The purpose is to remove an expensive instruction such as multiplication and use addition instead. This is also called induction variable elimination. And the idea is that we can predict the value of I, what value it will have several iterations in the future, since it's incremented by a constant expression. I will illustrate this now without SSA Form. And when we come to this optimization later in the course, we will do it on SSA Form. Okay, so what we do is to first translate this to 3 address code, and then we get this. And we say that we have basic and dependent induction variables. A basic induction variable is one which is incremented by a constant, and a dependent is one which is computed from a basic induction variable and with a constant. Okay, so basically we can see that S must be incremented by 4 each time. Then it will have the same value as it has already. I mean, we don't have to multiply by I, we can increment S by 4. Okay, so what we can do is to create this code. Whenever we increment I, we increment S as well, with the same amount as we multiplied I with. And of course, we insert an start value for S. Now we have the only use really for I is to check the loop termination. And we can, of course, get rid of that by using S instead. So what we do is to make a simple calculation and say that we should terminate this loop when S has reached a certain value. Okay, so how should we translate back from SSA form? Since computers don't have phi functions. It's not exactly like this, but essentially it's a very good first view. And that means this view is to create a copy statement for each operand. So if we have, that we show, if we have like this, A2 equals phi of A1 and A0 this time. Then, and here we have 2 basic blocks, and this one is there. So what we do is to instead use, so this is the original with SSA form, obviously, and then what we do is to create a copy statement like that and another like that, A0, and remove this one. This is not strictly true, but basically there is a fix needed in certain cases.